for NEET is now available on the Google Play Store. Try it out for free.
Hello students, we started catalysis in our last lecture and few of the most important things we studied about the catalysis. Today we will be studying about the enzyme catalysis, but before that I'll just summarize what we have learned in our last class. So just briefly I'll explain everything. So what we know about the catalyst or catalysis is the substance that accelerates the rate of a chemical reaction and itself remains chemically and quantitatively unchanged after the reaction is known as catalyst, and this process is known as catalysis. And the some examples that we have seen how the catalyst increases the rate of reaction. Why catalyst increase the rate of reaction? This is because catalyst reduce the activation energy required for a reaction or a chemical process to happen. So activation energy, so there is the reaction happens in many steps. So there we talk about the rate determining step, and if you remember chemical kinetics, so I have discussed about the rate determining steps. So many reactions like the complex reactions happens in many steps. And so all those steps, if you consider the barrier, the activation energy, the reaction with the highest activation barrier is known as rate determining step, that is the slowest process. So the catalyst, if a reaction is happening in a many steps, so catalyst reduces the activation energy barrier or the activation energy reaction barrier or activation energy for the rate determining step, and that is how it increases the rate of the reaction. And this is what we you can see from this. So this was the rate, suppose this is the rate determining step, or maybe this reaction happens in only one step, just you can consider from reactant to product. So this is the energy that this reactant has to surpass. This is the barrier this reactant has to surpass to get converted into the product. And suppose if you add one foreign molecule, with the addition of that foreign molecule, this activation energy is reduced. So now this reaction has to surpass only this barrier, the smallest barrier, this one. And so the rate of reaction will be faster. Now this is how the catalyst works. And further the mechanism that we have seen later on, and with the catalyst we have also seen the definition of some other inhibitors, some other molecules. And what are the inhibitors? As you see, the catalyst reduces the activation energy barrier. There are also some foreign substances. When they are there into the reaction mixture, they increases the activation energy barrier. And when they increase the activation energy barrier, such substances are called inhibitors. As the examples we have already seen, the promoters and poisons. We also talk about the promoters, or what promoters, some chemical substances that do not act as catalysts. They do not, if they are added in isolation, they will not increase the rate of the reaction. But when they are added with the catalyst, they increases the efficiency of the catalyst or the efficacy of the catalyst. And so such substances are called promoters. And this molybdenum for the iron catalyst in the Haber process for the synthesis of ammonia acts as a promoter, that we know. This chromic oxide and the formation of methanol from this water gas acts as a promoter for zinc oxide catalyst. So anyway, then there is the poison, the catalyst poison. Because there are certain substances where when they are added with the catalyst, they spoil the catalyst. They reduces the activity, either reduce the activity of the catalyst or they spoil the catalyst. So catalyst efficacy, its effectiveness is destroyed. So it doesn't now increase or catalyze the reaction. So such substances which spoils the catalyst, which destroys or reduce the efficacy of the catalyst, are called catalyst poison. Then we have seen certain process which we call autocatalysis, and autocatalysis is a process what we see in some of the chemical reactions. One of the products behaves as a catalyst, and such processes are called autocatalysis. And one the classical example that you know, the hydrolysis of ester. Hydrolysis of ester, we see the carboxylic acid is produced, and this acid actually helps in the hydrolysis of the esters, and so this is the autocatalyst. This is autocatalysis. This process is autocatalysis. Then we studied about the induced catalyst. These terms are important. That is why I'm just um, re-explaining those terms only. The examples you can read out and remember all the other terms. The induced catalyst is one reaction is happening. This reaction can happen, but there is another reaction which may not happen on its own. But when you just mix those two reactions or the reactants, and what you see, both the reaction now starts happening. So this kind of process are called induced catalysis. So one reaction is inducing the other reactions to happen, and so this kind of catalysis is called induced catalysis. Then we have studied about the catalytic process. So maybe of two types, homogeneous or the heterogeneous. Homogeneous catalyst and reactants are in the same physical state, same phase. So this is homogeneous, and you know homo means same. So if they are in the same phase, this is called homogeneous catalysis. And if you see this example, the both the reactants and this catalyst, they are all in the gaseous state. So this is an example of homogeneous catalysis. If you see this example, all the reactants, this is aqueous, sucrose in aqueous solution, it means it's a liquid, and this water and this acid, sulfuric acid, which is a catalyst, which is also in the liquid state. So they are all in the liquid state, and so this reaction is also an example of homogeneous catalysis. And then heterogeneous catalysis means that the reactant and the catalyst are in different phases. And what we know, if we see this example, this is an example of heterogeneous reactants are in gaseous state and the catalyst in the solid state. So this is an example of heterogeneous catalysis. If you see this example, the reactant is one. This reactant is in liquid state. This reactant is in the gaseous state, and catalyst is the solid state. So this is an example of heterogeneous catalysis. Some characteristics of catalysis we have seen, and the theory of catalysis we have seen the two theories. One theory, the intermediate compound formation theory, and this theory explains how homogeneous catalysts work. And this example we have seen. So for intermediate compound is formed, which is not very stable compound, which is unstable compound, and this unstable compound breaks to liberate the product and the catalyst back. So this is the intermediate compound theory. Then we have seen adsorption theory of catalysis. This explains the catalysis of heterogeneous catalyst, means the catalyst in the solid state and the reactants are in the liquid or the gaseous state. And this theory is nothing but adsorption plus intermediate compound formation theory plus desorption of the product. If you add everything, this becomes adsorption theory of catalysis. And this adsorption theory of catalysis, we have seen different steps. You can see here. First of the reactant molecules will come closer to the solid catalyst, then they will get adsorbed. After adsorbing, they will react and to form intermediate compound, and this intermediate compound will now break into the catalyst and the product, and you see they are broken into the catalyst and product, and then we see the finally it will go away from this catalyst to allow a space for new reactant to come, and so this is the process, this adsorption theory of catalysis. Then we have seen important features of solid catalyst, and first thing was activity. And when you talk about the activity of catalyst, the activity of catalyst is its ability to increase the rate of a particular reaction. The catalyst increases the rate of a reaction. Suppose for a chemical reaction, there are two catalysts which can catalyze this chemical reaction, and one catalyst, if the rate of reaction is higher in comparison to the other in the catalyst, so what we say, the first catalyst was more, its activity was more. So the activity of catalyst is its ability to increase the rate of a particular reaction, and the chemijobson is the main factor in deciding the activity of catalyst. This is what we have seen. Now, what is the chemijobson? With the chemijobson, what we see usually, if you see this figure, so initially now the chemijobson happens. These reactant molecules, they will have a chemical bond with the catalyst, and with that bond, what we see, that those bonds which has to be broken during a chemical process, they get activated in most of the cases when this reactants get absorbed to the solid catalyst, and once that gets, so those bond is gets elongated, so that bond has already broken to a certain extent, and so if that bond has broken to a certain extent, the barrier will decrease. And why this barrier? Because we know the region for the barrier in the chemical reactions. This is because why see for a chemical reaction to happen, we have to break certain bond, and to break that bond we need to require certain energy, and that is the barrier energy we see in the form of activation energy. And to break that bond, because the chemical bond formation happens with the release of energy, and so bond breaking will happen with the absorption of the energy, and that absorption energy we call the barrier. And if the bond has already become weaker, it means we need to provide lesser amount of energy to completely break that bond, and this is what we see, that bond is already, and that is called activation. So bond is already activated, now a new bond has formed, and once that new bond has formed, this bond that has to be broken, although in the symbolic form this mechanism is explained. So that bond, but this A is a compound, suppose it's a compound or it's a molecule, and suppose simply A is hydrogen molecule, so hydrogen molecule gets absorbed here. So hydrogen hydrogen bond, initially this bond is around, in the free hydrogen it is around 0.84 angstrom, and once it gets absorbed we see this bond is elongated, it becomes 1 angstrom or maybe zero point 0.9 angstrom, even if it becomes, so it is activated, and once this compound is formed we see this bond is completely broken and HH bond, and with that what once, so what we see, actually I wanted to explain this with the Chemistry option. We see the bond is already broken to a certain, is activated. Another thing is the Chemistry option, some energy will be released because that the chemical, partial chemical bond formation happens between the reactant and the catalyst, and that energy will also will be used to surpass the whatever the barrier that is there, to surpass that barrier, so the chemical reaction will happen. However, what we have to see, once this chemical reaction happens, the bond between product and the catalyst should not be very strong, so that the product will not dissolve from the catalyst surface. And so this chemistry option, whenever we see chemistry option, there should be balance between, this bond should not be so strong between reactant and the catalyst, that if this catalyst go and sit there even with the product, that bond between product and the catalyst is, should not be very strong. So this chemistry option should be there, should be a balance bond should between reactant and the catalyst should be strong enough that if the bond that has to be broken is activated, and also so a good amount of energy is released to surpass the barrier, but this bond between the reactant and catalyst should not be so strong that further this product molecules will not get dissolved from the surface to allow new reactant for the next phase of the reaction. So this bond should not be very strong, and this is what activity we talk about, and it's important. Then we talked about the selectivity of the solid catalyst as well, and the selectivity about the catalyst. What we know is catalyst. The catalysts are usually very selective. A catalyst which catalyzes one reaction may not catalyze is another reaction, and we have seen that a catalyst, even for the same set of reaction, different catalysts give different product. And you see this example, the water gas reaction with the hydrogen. I'm sorry. So water gas in the presence of copper catalyst it gives formaldehyde. Water gas plus hydrogen in presence of zinc and chromic oxide gives methanol, or the copper and chromic oxide gives methanol, or copper, or this thing, and all the water gas plus hydrogen in the presence of nickel gives methane plus water. So what we see, you are changing the catalyst with the same set of same reactants. This is carbon monoxide and hydrogen. It's a mixture of carbon monoxide and hydrogen. And we are getting three different products. This is because these catalysts are selective. They are selectively giving one product. And so the selectivity of a catalyst is defined as the ability of the catalyst to direct a reaction to yield a particular product selectively when under the same reaction conditions. Many products are possible that you can see here. So this is called the catalyst, the selectivity of the catalyst. And so solid catalysts are very selective. And these all these catalysts you can see they are solid catalysts. This is a nickel solid, it's a metal. This is also metal. Zinc oxide is also a solid, this is also solid. This is also solid. Also, this chromic oxide is what? It's a promoter for zinc oxide catalyst. Now, let's study about a selective catalysis by zeolites. Usually, when you study about a selective catalysis, the enzymes are also selective catalysts. So, the catalytic reaction that depends upon the pore structure of the catalyst and the size and shape of the reactant and the product molecules is called selective catalyst. What we know is this is a zeolite and it has certain pores, and in these pores, reactants of a particular size only can enter, they fit well, and so that they can undergo a chemical transformation. If the reactants are very small, perhaps they will not go reach to the active center of this catalyst, so they will not react, that the chemical transformation will not happen. And if the reactant is of the larger size, then it will not go inside the pores, and so the catalysis will not happen. So such catalysis is called selective catalysis. This is the JSM5 catalyst, the geolite, one type geolite. There are many types of geolite. This is JSM5 geolite. So the catalytic reaction that depends upon the pore structure of the catalyst So this is the pore structure of the catalyst, and this pore structure may depending on the different zeolites, uh, and the size and shape of the reactant and product molecules is called shape selective catalysis. And so the size of the reactants as well. And so the zeolites and enzymes are two common examples of selective catalysis. And the enzymes that we know, enzymes, what happens, enzymes are, they contain active sites, we'll see a little bit later. And in those active sites, only a substrate or the reactant for the enzymes are called substrate. A substrate of only a particular size and shape can only go and interact efficiently with the active site of that catalyst. And so only that substrate will undergo chemical transformation in presence of that particular enzyme. So enzymes are highly selective and they are selective catalyst. Because depending on the pore size and the size of that active site of that enzyme, the substrate of a particular size only they undergo a chemical transformation or they undergo catalysis. And so the zeolites are another example of the shape selective catalyst. And if you remember zeolites, we have seen in the mm, P block when we studied about the P block and zeolite, particularly the sulfur silicon family. So silicon oxide SiO2 silica, and in the silica usually what we see silica in silica each silicon atom is linked by four oxygen atoms, and each oxygen atom is linked to two different silicon atoms. And so if you replace some of the silicon atoms in the silica with the and just substitute those silicon atoms with aluminium, what we see in the silica Si2 silicon forms four bonds with four different oxygen atoms. So silicon is in plus four oxidation state. And if you replace that silicon with aluminium, aluminium can have maximum plus three oxidation state. There is one extra plus charge, positive charge ion is required, and those charges. So the net electrical neutrality, this silica becomes with the addition of aluminium negatively charged, and those negative charge are balanced by the alkali metals or alkaline earth metals, presence of cations, by the presence of alkali metal cations or alkaline earth metal cations. And now this compound is called what the zeolite. This is an example. Zeolites are formed in such a way. So zeolites are microporous aluminosilicates. So as I said, these are aluminosilicates with a three-dimensional network of silicates in which some silicon atoms are replaced by aluminum atoms, giving the ALOSI framework having honeycomb-like structure. So this has a honeycomb-like structure, and honeycomb has certain pores you might have seen. And so the reaction taking place in zeolites depend upon the size of reactant and product molecules. So what the reaction will happen, it depend on the size of reactant and the product as well as upon the pore size or the cavity of the zeolite. So this pore size will determine what kind of chemical reaction will happen, and not only that, it also what reactant and product will undergo the reaction and what will be the product. The product that will be formed, it depends on the size of the reactant and the product molecules. And so they are found in nature. The zeolites are found in nature as well as they are synthesized for catalytic selectivity. So zeolites, there are many examples of zeolites, and zeolites being widely used as a catalyst in petrochemical industries for cracking the hydrocarbons and isomerization. So for cracking of hydrocarbons and their isomerization, we use zeolite catalyst. One example you can see, an important zeolite catalyst used in the petroleum industry is JSM5, which converts alcohol directly into gasoline by dehydrating them to give a mixture of hydrocarbons. And so this GSM5 is used as a catalyst in the petrochemical industry or petroleum industry. Now let's see enzyme catalysis. And as I said, enzymes are also catalysts. First of all, let's understand about the chemical nature of enzymes. So what you might have heard about the proteins. Proteins are made up of amino acids. The polymers of amino acids are called proteins. And when initially the polymer of amino acids they form a peptide, polypeptide, these polypeptides they fold together to form, and these polypeptides are called primary structure. These polypeptides they fold together to form secondary structure. Some examples of secondary structure you might be knowing: alpha helices, beta sheets, and so on. And now this secondary structure they further folds to form tertiary structure, which is the active structure of an enzyme, that we call three-dimensional structure, or tertiary structure becomes three-dimensional structure. And now that structure acts as an enzyme. We also see further segregation of different units that we call quaternary structure. As you can see, the hemoglobin, four different subunits they form together. The four subunits of hemoglobin have, that we call the quaternary structure. So usually enzyme is the tertiary structure, or that we call also the native structure of a protein. And in that native structure, what we see usually some other groups they come and join to the enzyme at certain position, and those groups are called the coenzymes, or sometimes prosthetic group, when they bind completely very strongly. Usually, what we see many enzymes like cytochrome P40, some heme group, copper heme complex with the porphyrin ring, that we also call heme group, that go and joins there. Like hemoglobin, that is also prosthetic group, that is attached permanently to the enzyme. So they are called prosthetic groups, and there are some chemicals which go and attach to a protein for a particular period of time. They are called enzymes. So they in bond between coenzymes and the protein is very weak, and once the coenzyme of prosthetic group get attached to this tertiary structure of the protein, this entire structure now is called enzyme, which is the active catalyst. So enzymes are protein molecules, and these protein molecules, amino acids, were chemically you understand. This is has carbon atom, and carbon atom is associated to one carboxylic group, one amine group, and one R alkyl group is attached to it. So this structure is called amino acid. So there are many 20 types of amino acids, and with different combination they form one protein. So enzymes are protein molecules of high molecular mass, which are produced by living plants and animals. They form colloidal solution in water. This colloidal solution in water they form, this you should understand. So these proteins are of certain size, and one molecule of the protein having a certain size, it forms colloid. So this they form colloid, but this in this colloid each particle is one protein molecule or one enzyme in the water. So they are very effective catalysts. They catalyze numerous reactions connected with living processes, and most of the reactions that happens in our body, because of which we are surviving, actually are catalyzed by enzymes. Different types of enzymes, around more than 3,000 enzymes are there in human body, and because of the presence of those enzymes, we are surviving. If certain enzymes and some enzymes stops working, so our survival will become very difficult. And since, as you know, the vitamins works as coenzymes, so that is why we need vitamins for our survival as well, because as those enzymes, coenzymes are important for the functioning of that enzyme. And if that coenzymes are not there, means the vitamins are not there, so they will not get attached to a protein to become make that an enzyme, active enzyme. So that chemical process which it was catalyzing will now stop happening, and our survival will become difficult. We get certain diseases, and so so the enzymes are very effective catalysts. They catalyze numerous reactions connected with living processes. Numerous reactions that occur in the bodies of animals and plants to maintain the life processes are catalyzed by enzymes. The enzymes are known as biochemical catalysts, and thus why? Because they catalyze biochemical processes. And the chemical processes which happens in the biological systems are called biochemical processes, and since they catalyze biochemical processes, they are called biochemical catalysts. And thus catalysis by enzyme is also known as biochemical catalysis. Many enzymes have been obtained in pure crystalline state from the living cells. So earlier people started crystallizing these enzymes as a protein structure. However, recently we also know how one can synthesize an enzyme. And the first enzyme that was synthesized in the laboratory was in 1969. For the first time, a human get successful in synthesizing an enzyme in 1969. However, for a long time, people used to crystallize those enzymes, and now if you look at the examples of the enzyme catalysis, is the first example is inversion of cane sugar into glucose and fructose by the invertase enzyme. So invertase enzyme converts this cane sugar it's a sucrose, and this sucrose is a dimer of glucose and fructose. So the glucose and fructose molecules, they when they link together with the glycosidic bond, what is that glycosidic bond and how they are linked together, we'll see this in the biomolecules chapter. So just understand this is dimer means this is also a monosaccharide. This is also a monosaccharide, and these when those two monosaccharides join together, we can say this they form disaccharides. So this is a disaccharide. So cane sugar or the sucrose is a disaccharide, and this disaccharide it requires water molecules to get hydrolyzed into glucose and fructose. And this reaction, because this O C bond has to be broken in this reaction, and to break this bond, we require a catalyst, and this catalyst in the biological process is the invertase enzyme, and the source of invertase enzyme is yeast. Now you see another example conversion of glucose into ethyl alcohol by gymase. These are simple reactions that are known to, but all the chemical reactions that we know in the oxygen bound bind to this hemoglobin that carries one of the protein, it carries there, and its oxygen goes, and with the oxygen the uh, glucose is oxidized in the presence of oxygen in our cells. Some of the reaction will happen into the mitochondria. Most part of this reaction, the oxidation of glucose happens in the mitochondria, and energy is released. And that is why we also know the mitochondria is called powerhouse of the cell. A mitochondria is one of the cell organelle, one part of the cell. If those who do not understand, particularly a student from the J side. So what we see the conversion of glucose into ethyl alcohol by enzyme gymase, and this is the glucose C6H12O6. We know the chemical formula, and this in presence of enzyme gets converted into ethyl alcohol or ethanol plus carbon dioxide, and so this carbon dioxide molecules are formed here. Now so the enzyme here is gymase. The conversion and the source of gymase enzyme is, you can see here, it's also yeast in this table. So conversion of a starch into maltose. Maltose, as we have seen, the sucrose. Sucrose is disaccharide. Similarly, maltose is also a disaccharide, and this is disaccharide of alpha D glucose. So two alpha D glucose molecules they join together to form maltose. So there also that the glycosidic bond happens between two alpha D glucose molecules. And what is from where the term alpha and D comes in the glucose, and what is the structure of glucose? The structural formula we will see again, as I said, the biomolecules chapter. Here you can just find out. And so the conversion of a starch, what is a starch? It is a polysaccharide, and polysaccharide of alpha D glucose one can say. So the polysaccharide one can understand, and and so and this is disaccharide, as I said, this maltose is disaccharide of alpha D glucose, and this is polysaccharide. So there are many alpha D glucose units that are joined together. They may form one chain or the branch chain, depending on what form of a starch it is, amylose or amylopectin. And so this is an starch, and one can write the general formula for a starch C6H10O5N. This N is in the subscript. I should write here in the form of subscript. And so in such units, okay, and in such units are there. So this is a starch. And now a starch, when this starch reacts with n molecules, if the n such units are there, and so we need n water molecules in the balanced reaction, and this enzyme in the presence of diastase enzyme. So diastase enzyme catalyzes this reaction, catalyzes the hydrolysis of a starch into maltose, which is a disaccharide, and so n molecules of maltose are being created. So what we see this N molecule, and so convert now the another example of enzyme catalysis, conversion of maltose, this maltose into glucose by enzyme maltase. So maltase enzyme converts this maltose, the disaccharide, into two molecules of glucose. So a balanced chemical reaction should have two here. So the two molecules of glucose will be formed. So this is a maltose. A maltose, as you can see, the chemical formula of maltose and sucrose will be same for the cane sugar C12H22O11, C12H22O11, because they are both disaccharides and they are both made up of the hexose sugar. Glucose is also a hexose sugar, or fructose is also a hexose sugar. Hexose sugar means the sugar containing or the monosaccharide containing six carbon atoms. So this is a hexose sugar. It also contains six carbon atoms, and you can see the fructose and glucose. Although the chemical formula is same, but their structural formula is different. So one can say they are isomers. So they are isomers. The maltose and uh, sucrose, they are not isomers, but they are different molecules, different compounds. So now what we see, this the maltase enzyme converts this maltose into glucose, two molecules of glucose. And so this conversion is the hydrolysis of maltose to glucose in presence of maltase enzyme is also a biochemical process. And this maltase enzyme, source of this maltase enzyme is also yeast. And diastase enzyme is malt. Now the decomposition of urea into ammonia and carbon dioxide by enzyme urease. So urea is there and urea is also hydrolyzed in presence of urease enzyme into ammonia and carbon dioxide. So this is the urea molecule NH2CONH2 and the functional group you know it's amide. So because CONH2 the functional grouping we call amide plus H2O and urease and one can see this NH2 group is amine, but if CONH2 bond is there, it's more closer to amide group, although it has also one extra NH2 bond. So anyway, so this decomposition reaction, this is also a hydrolysis kind of reaction. It's not a simple decomposition, it's a hydrolysis in presence of urease enzyme. And so to form and what is formed is ammonia and CO2. This is also a biochemical process catalyzed by urease enzyme. So urease is the enzyme. In a stomach, what we know, the pepsin enzyme converts proteins into peptides. So whatever protein sources that we take, food we take, and what these proteins goes into the stomach, and in stomach the pepsin enzyme is there. Pepsin enzyme converts these proteins into peptides, and some of the proteins which are undigested goes into the intestine, because after the stomach intestine starts, and in that intestine the pancreatic trypsin. So the source of this trypsin enzyme is the pancreas. So pancreas secretion from the pancreas, this trypsin comes into the intestine, and then trypsin converts the proteins into amino acids by hydrolysis. And so this is also hydrolysis. The breaking of enzyme is the hydrolysis process, because you are breaking something in presence of water. So water molecules are being used to this process is hydrolysis. All these processes that we have seen, they are hydrolysis process wherever the water is used. This is a simple conversion, chemical conversion. One can consider this as a simple decomposition as well. This is also a hydrolysis process. So the hydrolysis usually the digestion, and all the digestive enzymes are, that is why called hydrolase, because they do hydrolysis. So they are called hydrolase. And the hydrolase enzymes you see, the lipase enzyme, it help the breaking of fat, amylase enzyme, breaking of this um, amylase carbohydrate food. And then we see the proteases, all of the enzymes, this is a common class of proteases. The enzymes hydrolyzed proteins are called proteases, and that is examples that we have seen. The pepsin and trypsin, they are examples of proteases. So they are also hydrolyzed. And now the another example is conversion of milk into curd is an enzymatic reaction brought about by the proteolytic enzymes. These are also proteolytic enzymes or the proteases produced by lactobacilli bacteria present in curd, used as a starter culture. So whatever the curd we use as a starter culture, it contains lactobacillus bacteria, and the plural of bacillus is bacilli. And these lactobacillus, they are present in milk, and bacillus means they are rod-shaped bacteria, and they convert milk into the curd. So they produce certain enzyme, and those enzymes break amino proteins into amino acid, and finally it converts milk into the curd. There are also this lactococci. Cocci are spherical bacteria. Coccus are a spherical one bacteria. It has a spherical shape. I think there are many bacterial colony we call cocci, and they can also they convert milk into cheese. So those reactions you perhaps know, the conversion of milk into the cheese catalyzed by lactococci, conversion of milk into curd catalyzed by lactobacilli. Bacilli rod-shaped bacteria, their shape is like a rod, and cocci are spherical shape. And those who are from biological background, they may study. I don't know whether it is there in your syllabus, but you may read it in your biology class. So enzymes, let us now see some of the enzyme and their source and enzymatic reactions. So this is summarized here. So now the invertase enzyme. The source is yeast. Yeast, we know it's a fungus, our unicellular fungus. Fungi, and the source, what it converts sucrose into glucose and fructose. The gymase enzyme, the source of gymase is also yeast, and if this gymase converts glucose into ethyl alcohol and carbon dioxide, this reaction we have already seen these two reactions. The diastase enzyme, the source of diastase enzyme is malt, and this diastase enzyme converts starch into maltose. Maltose, which is also a disaccharide like sucrose, but this is disaccharide of alpha D glucose, and this is disaccharide which is made up of alpha D glucose as well as fructose. Now the maltase enzyme, the source of maltase enzyme is yeast, and this maltase enzyme converts maltose, which is a disaccharide, into two glucose molecules. Now this urease enzyme, the source of urease is soybean, and this urease enzyme converts urea into ammonia and carbon dioxide. The pepsin enzyme found in the stomach converts protein into amino acids. So this pepsin enzyme is a protease. Let us now see the characteristics of enzyme catalysis. So enzyme catalysts have certain characteristics. We have seen the certain general catalyst, chemical catalyst also have certain characteristics. Apart from those, enzyme catalysts have certain more catalyst characteristics. And what are they? So the most highly efficient catalyst. So the enzymes are most highly efficient catalysts, and they are so catalyst that one molecule of so efficient that one molecule of an enzyme may transform 1 million molecules of the reactant per minute. The example you can see that the catalase enzyme can perform nearly 88 lakh catalytic events per second. This is around 1 million. This is per minute. I am saying that this catalytic reaction is 8,000.18 million per second. So once this catalase enzyme is one of the most efficient enzyme, and this enzyme actually converts H2O2 that is produced in our body into oxygen and water. The peroxides, they are not very good for our body, induce aging. So the catalase enzyme is there, and it converts H2O2 into water and oxygen molecules. And what we know, the H2O2 has its potential to get converted into water or oxygen molecules, but that reaction will be very slow. It will take a lot of time, and by that time, this H2O2 may get converted into some other product, and it may oxidize many of the other things. Because this H2O2 has potential to get reduced with oxygen, the has potential to go into -2 oxidation state, and in the peroxide H2O2 is what in the peroxide means H2O2 oxygen is -1 oxidation state, so it gets converted into -2, so it will oxidize something else, and so this because of that the aging many other side effects will be there. So this catalase enzyme catalyzes that reaction, and its catalytic is a very efficient enzyme, and it does almost 8 lakh events per second. The enzyme catalysts are also very highly specific in nature and highly specific. The specificity that we have seen, or the selectivity. Specificity means the selectivity. So they are highly specific. They are very selective. So each enzyme is specific for a given reaction. So they are very selective. That is, one enzyme cannot catalyze more than one reaction. Usually, for example, enzyme urease catalyze the hydrolysis of urea only. It does not catalyze hydrolysis of any other amide. So as we have seen here, the urea is hydrolyzed by urease enzyme, and this is amide. If there is some other amide, so this urease enzyme will not hydrolyze that amide, and it will and to convert it into ammonia and CO2, or maybe some other product depending on the chemical structure of that amide. So, but it does not convert, it does not catalyze those reactions, and so you can see how specific an enzyme can be, or how selective an enzyme can be. The enzymes are highly active under optimum temperature. So optimum term comes. So under a certain, it's only a very small temperature range, enzyme activity is highest, and that temperature range we call as the optimum temperature of enzyme activity. So what we see, the rate of an enzyme reaction becomes maximum at a definite temperature called the optimum temperature. That definite temperature we call as optimum temperature. If you see this graph, rate of reaction catalyzed by an enzyme and this temperature. As you increase the temperature, initially the enzyme activity, the rate of reaction is increasing, and at a certain time, you see here we get the peak, and then the rate of the reaction reduced very fast. And this temperature and this range, around this range, we call the optimum temperature For humans, it's close to 37 degrees centigrade. The human body is close to 37 degrees centigrade, the temperature. And this energy up to here, what happens? The heat energy causes more collision between enzyme and substrate. So more collision between enzyme and substrate happens because heat energy to increase the heat up to here. And once you increase the heat to a certain extent, what happens now? Enzyme structure denatures. So usually proteins, as you know, I said the enzymes are basically proteins, and some enzymes are also RNA, which we call ribozymes. So these enzymes are mostly most of the enzymes are proteins, and these protein molecules, what we know, they get folded, these polypeptides, because of the very weak bonding that you can. Some of the bonding is the hydrogen bonding that we know. Very weak bonding, they get folded to form a three-dimensional tertiary structure. And if you increase the temperature, what happens? These weak bonds, they are broken, and once these weak bonds are broken, this protein molecule will get some other structure, and that structure we call the denatured structure. It is not the native structure of the protein in which it was acting as a catalyst. So it is not a native structure of the protein, and this process we call the denaturing of the proteins of the enzymes. So enzymes at higher temperature, they get denatured. So they denatured means they get some other structure which is not an active structure of the enzyme, and so the since enzyme has its active structure, most of the as you increase the temperature, it is keep denaturing, and so what happens with increasing temperature, the enzyme activity reduce very fast, and you see around 60 degrees centigrade temperature, enzyme activity becomes zero. So one cannot, a human beings cannot survive above 60 degrees centigrade for the human enzymes. However, we have seen that certain bacteria, they even survive at 100 degrees centigrade, and those bacteria also contain certain enzymes, and because they are also life and some biological processes or life processes to happen, they also require certain enzymes. Those enzymes in the thermophilic bacteria, they are even stable there because of some other molecules that are there in their body, and so they get thermal stability. We call some because of the presence of certain accumulates that not part of your syllabus. So anyway, what we see, the high heat energy initially causes more collisions between enzyme and substrate. With the higher temperature, this collision will increase, but now the enzyme has lost its native functional structure. So this catalysis will reduce. Although this heat, the collision will be more, and the even some of the but the effective collision will reduce, because for the effective collision, enzyme has to certain structure, and in a particular orientation only that collision has to happen, and that effective collision is reduced, although with the number of collision is increased at higher temperature. So the enzyme activity is reduced uh, after certain temperature, and this temperature is called the optimum temperature. On either side of the optimum temperature, as you can see in this graph, the enzyme activity decreases. The optimum temperature range for enzymatic activity is 298 to 310 Kelvin. This is 25 degrees centigrade to 37 degrees centigrade around. So this is optimum temperature range. In human body, temperature being 310 Kelvin is suited for enzyme catalyzed reaction. So 310 Kelvin, the average temperature. Some people are slightly lower, some people body temperature is slightly up. So this is 310 is around 37 degrees centigrade is average body temperature of a human being in normal condition if that person is not having any fever. So what like the temperature, the optimum temperature enzymes also work effectively under an optimum pH, and the pH particularly other than and so the rate of an enzyme catalyzed reaction is maximum at a particular pH range, and that pH range we call the optimum pH, which is between pH usually between pH value 5 to 7, other than the enzymes which work in the inside the stomach. And stomach, the concentration of HCl is around 0.03 molar and 0.03 molar, and this concentration changes if you drink water, a lot of water, and if you have a food, this concentration reduces. So with that, what is usually and so the pH of in stomach of human beings usually changes between 1.5 to 4.5. So under this pH, some enzymes work. So, but what we see other enzymes, usually you see the lipase, protease, amylase, they are all the hydrolases, they are digestive enzymes. The lipase, as I said, lipase, it hydrolyzes fat. Now the breaks fat. This proteases, they hydrolyze protein. Amylase, they hydrolyze starch and converts it into glucose. This protease converts into the amino acids, proteins into the amino acids. So all sides of proteases. This is amylase, they are class of enzymes. There are many enzymes that are proteases. In the amylase, there are class of enzymes. There are many enzymes that work as amylase. So usually, as you can see in this graph, at the very lower temperature, enzyme activity is almost zero. And after a certain pH, you see the enzyme activity started shooting up, and at a particular pH, the activity is on between 5 to 6, and the activity is for these three enzymes, activity is optimum, the amylase, protease, and lipase, and so, and then after that, the this activity, the enzyme activity again starts reducing. And as I said, depending on the enzyme, this optimum pH may vary slightly. So for these three enzymes, we see the optimum pH is 5 to 6. For some other enzymes, it may be slightly lower than that, and some other enzymes may be around 7. So usually for the average, most of the enzymes, this pH range, optimum pH range value is 5 to 7, as we see in this graph. 5 to 6 for these three enzymes. The optimal pH may depend on the type of enzyme and function, as I said, and usually digestive enzymes work at little lower, not at the pH. So, and why this at very low pH this enzyme doesn't work? This is because at the very low pH you will have hydrogen ion concentration very more, and it means what will happen is enzyme contains many NH2 groups, and all those NH2 groups and even the free carboxylate groups, COO groups will be in the free form in most of the cases if they are on the surfaces mostly, and because the water molecules at a 7 pH, our body pH is around 7, so I think it's a Mm, mm. And so what happens? So what happen? This all these three groups, COO groups and NH2 groups, will be now in the protonated form. And since the COO minus 3 COO minus group carboxylase group many places is catalyze certain type of reactions, or if it is there in the free form in the active site of the enzyme, it actually interaction, and it also creates some electric field, and those electric field electrolytic catalysis we also see. But once this entire thing becomes neutral, the electrolytic catalysis or maybe other function that it was working will stop working, and so at the lower pH what we see the enzyme catalysis this is not there. And what we see at the very high pH, the solution becomes, once it becomes basic, what happens? Most of the what happens, the group, the three groups will how they will be deprotonated. Even NH2 groups which became NH3 plus, like the basic amino acids are there. They are like arginine, lysine. So those basic amino acids will also be deprotonated. Histidine works in the is found in the active sites of the active site pocket of many enzymes that will also be deprotonated. So that very high pH also the enzyme lost its activity because the deprotonation of the many useful groups, and at the low pH enzyme stops working because of the protonation of some of the useful groups that were acting as a which were catalyzing the reactions and were found in the active site of the catalyst. The next characteristic of an enzyme is increasing activity in presence of activators and coenzymes. So the enzyme activity is increased in the presence of certain substances known as coenzymes. And coenzymes and some, as I said, and there is another term for prosthetic group. So it has been observed that when a small non-protein, a non-protein like vitamins, is present along with an enzyme, the catalytic activity is enhanced considerably, and then in the presence of these vitamins, so these vitamins are called, or whatever the extra molecule that when get attached to the protein part of the enzyme, the activity of that proteins increases, the enzymes increases. This is called a coenzyme. What we see that some groups also get attached permanently to that protein molecule. They are called prosthetic group, and they are also very important for the catalytic processes. And usually those groups are the active center. They are usually found in the active site pocket of the enzyme. And what is the active site pocket? The portion of the enzyme where the chemical changes happening and where the chemical reactions are happening, substrates get converted into the product, that is called the active site. So a certain pocket has certain empty volume. And so the activators and the coenzymes, the some of the activators means they are metal ions, are the Na plus ion, Mn2 plus ion, cobalt ion, copper 2 plus ion, so cobalt 2 plus ion, they contain the copper 2 plus ion. As I said, the cytochrome P450, it contains copper ion. Some of them activators are also iron 2 plus and so on. The so these metal ions, when weakly bonded to enzyme molecules, increase their catalytic activity. So when they are bound to the enzyme molecules, they increase their catalytic activity. For example, amylase in the presence of sodium chloride. And what is sodium chloride in the aqueous solution like that we see inside the human cells or any of the living cells around 7 pH, so it will be Na plus and Cl minus in the presence of water in the aqueous solution. So the Na plus ions are catalytically very active, or very important for the amylase enzyme. So the amylase enzyme activity increases in presence of Na plus ion. So the for the amylase enzyme, which does what function? It breaks starch into glucose, and so this activity is enhanced in presence of Na plus ion. So what we see, the other example is, so this is Na plus ion is activator for the amylase enzyme. Now, the influence of inhibitors and poisons, like other catalytic processes that we have seen in the laboratory, the reactions happening in the laboratory, the enzymes, the reactions that happens in the biological system. So the catalysts are enzymes. So there, these enzymes also have inhibitors and the poisons. Like ordinary catalysts like that we use in the laboratory or the industry, enzymes are also inhibited or poisoned by the presence of certain substances. The inhibitors or poisons interact with the active functional groups on the enzyme surface and often reduce or completely destroy the catalytic activity of enzymes. So inhibitors or the poisons, what do they do? Inhibitors are like we see the enzymes has certain coenzymes or the promoters or activators. There we have seen the promoters that we say for the enzyme for the catalyst that we use in the laboratory or the industry. The promoters are there. For in the case of enzyme, the term is coenzyme or the activators. But there we have seen inhibitors or the poisons. Here also the inhibitors and poisons are there. And so the some molecules, when they bind, get attached to the protein at certain positions, they destroy the activity of enzyme completely, or they reduce the activity of enzyme, and such molecules are called inhibitors or poisons. The use of many drugs is related to their reaction as enzyme inhibitors in the body. So what happens? Some reaction process, suppose you have certain problem and this life process is happening in certain direction. To break that process because of which you got the disease, and if you want to stop that process, what you do, the enzyme that was catalyzing that reaction, that chemical process in that direction, you will use a certain drug which can stop that chemical process to happen in that direction. So now this drug will go and bind with that enzyme in such a way that it is that enzyme becomes unfunctional, and so the drug may work in that direction. So this is one example. So many drugs is related to their action as enzyme inhibitors in the body. Let us now study about the mechanism of enzyme catalysis. So there are a number of cavities present on the surface of colloidal particles of enzyme. As I said, the number of cavities, some of the cavities is the larger and the functional cavity, which we call the active site. So these cavities are of the characteristic shape and possess active groups such as NH2, COOH, SH, OH, etc. Usually on those sites, this exists in the form of NH3 plus, and this exists in the form of COO minus. As you know, at the 7th pH, this pK value of COOH group is around 4.5. So more than 50% of COO minus group will be around. It will be hydrolyzed. At the 7th pH, it will be means around 90% will be in the form of COO minus, and similarly NH2 group will be in the H plus. So this H plus goes to here. So this will be protonated, and this will exist in unprotonated form in the active sites, which if it is on the surface or wherever, if it can interact with the water molecules of the solution or of the cell, that is there into the cytoplasm. So water molecules are there in the cytoplasm. So there, there are actually the active centers on the surface of enzyme particles, and these active centers are called active sites. The molecules of the reactant which have complementary shapes fit into the cavities just like a key fits into lock. And so this is what we call, this is also shape selective catalysis, and you see the shape here, like this we call the lock and key model for enzyme action. And so this is a shape selectivity. So according to whatever the active site is shape under the structure it is there, certain molecules only go and fit there accordingly, and those molecules and that we call the reactants, and the reactants that we do use talk about in the chemical process, in the enzymatic processes, we call that as a substrate. And these substrate molecules, they will go and fit there into the cavity, and then they will undergo a chemical transformation and get converted into the product. So this have the completely shape, and it fits into this cavity just like a key fits into a lock. This is just a very rough example. If you see the real structure of an enzyme and the substrate, how it binds, you may get a better feel, but this is for the initial understanding. This is quite a good model. So the substrate interacts with the active groups present in the active site. So on the active site, some active groups, as you see, these groups are there. These are the COO minus and NH2 plus. If I can write this COO minus, that will be better at the 7 pH. Or these are nothing but this is because this gets deprotonated and this gets protonated. This is an acid, this is a base. So base will abstract this COO minus ion, and so this will exist in this form mostly. So this substrate interacts with the active groups present in the active site, and whatever the substrate will have certain atoms which can interact with this. If this is positively charged, if the negative center is there on the substrate, it will interact with this, and if the positive center is there on the substrate, it will interact with the negative center of the active site, and so on. Or if the hydrogen bonding tendency is there, so there will be hydrogen bonding formation, and so on. So they will interact with the groups present in the active site, and thus an activated complex is formed that decomposes to yield the product. So an activated complex will be formed, and that activated complex, as we have seen for the catalytic reaction, that activated complex and that intermediate complex that we have seen, this complex will be now broken into the enzyme and the product. And so this will be broken into the products, and so the enzyme finally will be liberated. So as you can see here, this is an enzyme which is key, and the substrate is the lock, and that for a particular lock we have a particular key. So once this key is attached to this lock, or means this enzyme is attached to the substrate, then this will fit there, and this interaction will happen at this site. And this site, for if this is enzyme, you can say this site for the enzyme is the active site of the enzyme. Usually, as you can see here, the substrate is shown in the bigger size and enzyme is smaller in size, but in reality, enzymes are much bigger than the substrates. So as and this further to explain the lock and key model, the substrate is shown in the larger size because locks are larger in size than the key. But in reality, enzymes are much larger, much bigger than the substrate, and substrates are only small molecules that go and fit there into the enzyme. And so once this happens, the substrate will broken into the product, and this E plus A, the enzyme and substrate, they form this activated complex, enzyme and substrate complex, and this enzyme and substrate complex will now broken into enzyme plus product. So this product plus enzyme get separated. These are the products. So thus what we see, the enzyme catalyzed reaction may be considered to proceed in two steps, and this one step is this, another step is this. This step we call is in equilibrium. So enzyme interacts with the sulfur, and the formation of enzyme substrate complex is in equilibrium, and then next step is it goes into the forward direction, and based on this one can also find out the expression for the rate constant and so on. The Michaelis-Menten constant that is there, but this is not in your syllabus. So the two steps that enzymatic reaction that may happen in two steps is this. So binding of enzyme to substrate to form an activated complex. So enzyme binds to substrate to form an activated complex. This is dagger is an activated complex, and the second step, the decomposition of the activated complex to form the product. So this activated complex decomposed into the product and an enzyme, and here we get the enzyme separated. So now let's see the catalyst because everything we have, even the enzymes are the example of catalyst, and they are shift selective catalysts like zeolites. So let us talk about some catalysts in the industry. So some of the important technical catalytic processes are listed in this table. So this the Haber process that we know for the synthesis of ammonia, and this ammonia is important for the formation of urea. So Haber process, this reaction we see the nitrogen reacts with the hydrogen, three molecules of hydrogen to form two molecules of ammonia, and this reaction has to be catalyzed, and this reaction is catalyzed by finely divided iron, and this iron catalyst is actually made more efficient in the presence of molybdenum as promoter. So molybdenum enhances efficiency of this iron catalyst. And the condition for this process, the industrial condition that we provide in the industry is 200 bar pressure, the very high pressure that we apply. And why we apply very high pressure? Because this reaction is an equilibrium, the reversible reaction, and we apply very high pressure for the Le principle. And what we know, the number of molecules are reduced in the product side. So if you increase the pressure, this reaction will try to get into the direction to reduce that pressure, and to reduce that pressure, the number of gaseous molecules will go in the direction. When the number of gaseous molecules will decrease in the forward direction, so this reaction will get converted in this direction. So we use very high pressure and 723 to 773 Kelvin temperature. Nowadays, a mixture of iron oxide, potassium oxide, and alumina is also used. So iron oxide mixture instead of this. Now people are also using iron oxide, potassium oxide, and alumina oxide as a catalyst. Now the second important process is the Ostwald process for the manufacture of nitric acid. So the nitric acid, and this is catalyzed by platinized asbestos, and this temperature at which this reaction happens, also Ostwald process, which is the industrial process for the formation or for the synthesis of nitric acid. The temperature, the favorable temperature is 573 Kelvin. So what we starts with the ammonia, and this ammonia, when so what you see, the this ammonia is useful in the form of synthesis of urea, as well as you can also start with ammonia and form the nitric acid. So the Ostwald process starts with ammonia and five this water oxygen molecules. So dioxygen, so it interacts with dioxygen to form nitric oxide plus water molecules. And now this nitric oxide that is produced in the first step now it reacts with oxygen to form NO2 gas, nitrogen dioxide gas. And nitrogen dioxide gas, when it reacts with water and oxygen, it forms nitric acid, and this catalyst, this reaction happens in the presence of platinized asbestos at this temperature. So this is the Ostwald process. This is Ostwald process. The next process is the contact process for the manufacture of sulfuric acid, that we know contact process, and with this process the sulfuric acid is manufactured, and in this case also we use catalyst platinized asbestos. What this platinized asbestos are actually poisoned by the arsenic impurities that is there with the gases, which reacts to form this um, sulfuric acid. So people nowadays people are using vanadium pentoxide as a catalyst. So V2O5 is now preferred as a catalyst. So this could be even the platinized asbestos or vanadium pentoxide could be a catalyst for this contact process. So this contact process is sulfur dioxide gas reacts with oxygen to form sulfur trioxide gas. This is an example, as you can see, the heterogeneous catalysis. This is also heterogeneous catalysis. This is also heterogeneous catalysis. The industrial processes that you see, they are heterogeneous examples of heterogeneous catalysis. The heterogeneous catalyst means are more efficient than homogeneous catalyst usually. So the sulfur trioxide gas is formed, and now the sulfur trioxide gas reacts with sulfuric acid, one molecule of sulfuric acid to form oleum. And this H2S2O, this is a highly concentrated, can say highly concentrated sulfuric acid. And this oleum, when you dilute it with the water, you can get the one oleum when it reacts with one water molecule. You see combination of two molecules of H2SO4 and the oleum, and other things about this will also study in volumetric analysis and so on. So with this, I stop this topic, the catalysis, and in the from the next class we will start colloids. And about the colloids, the many important points in the colloids, in the colloidal form, many catalysts that we use, And this catalyst, whatever this catalyst that we use, we try to use those catalysts if they are in the colloidal form or if they are in the very finely divided particles. And so I'll stop this class here. We'll meet again in the next class. See you then. Bye.